Okay, so this brings us to what are known as the simple gas laws. There are 4 basic properties of a gas. Pressure, abbreviated with a capital P, volume, abbreviated with a capital V, temperature with a capital T, and when we talk about an amount of gas, we usually refer to the amount in moles, and that's given the symbol lowercase n. Don't ask me why. So these properties are interrelated. If you change one, then one or more of the others is going to change as well. The simple gas laws describe relationships between pairs of these properties. So they are simple gas laws because they only consider 2 properties at a time. So you can look at the relationship between pressure and volume, or between amount of moles and pressure, or between temperature and volume. Just looking at 2 things instead of all 4 of them at the same time. So the first one was described by Robert Boyle back in the 1600s. Now, it's good to be familiar with these guys' names. I think the history is pretty fascinating, but I am not going to say on an exam, what is Boyle's law? Not going to do that. I don't think that's useful. You should be able to use Boyle's law, but you don't have to remember his name. So what Boyle did is he used a J-shaped tube with mercury in it to investigate the relationship between the volume of a gas and the pressure of a gas. So he's got a gas in this one side, and this is sealed off, and he can measure the pressure difference, just like with the manometer, by measuring the difference in the heights of the columns of mercury. So then what he would do is he would pour more mercury into this side, which would put more pressure on this gas. The gas would get squished, but the pressure is larger because the height difference is larger. So he could put pressure on the gas just by adding more mercury to the tube. Then he could measure the volume of this gas. And so he could look at the relationship between the volume of the gas trapped in here and the pressure. And what he observed is that there was an inverse relationship. When the pressure is higher, the volume is smaller, and vice versa. So scientists like to graph data, and we don't do this just to be perverse or confusing. We actually do this because it's easier to see what's going on when you look at the relationships on a graph rather than just looking at numbers. So here's the volume of the gas as the pressure changes. And we see that the volume was initially quite high. As the pressure increases, the volume gets smaller and smaller. Now, this is not a linear relationship. This is a curve, right? We like to manipulate the graph so that we can get a linear relationship, because then we can use linear regression and find the equation for the line and get a nice equation out of this. So what Boyle discovered was that the volume is inversely proportional to the pressure. And when we look at these 2 variables, volume and pressure, we assume that we're holding the other 2 constant. We're keeping the same temperature and the same amount of gas. And so this is how Boyle's law is generally stated. P1V1 equals P2V2. So earlier we saw a graph of volume versus pressure, and that was a curve. If we graph volume versus 1 over pressure, we get a straight line. And that's illustrated here. So this is volume versus pressure, and here we're graphing volume versus the inverse of pressure. And that gives us a really nice straight line. So a molecular interpretation of Boyle's law, more of the theory, what's going on, why does this work? So here we have a container. We've got a movable lid here and a pressure gauge. So here we've got a volume of 1 liter and the pressure is 1 atmosphere. And notice we've got the same number of little green gas particles in each of these containers. If we increase the weight that's sitting on top of this container to press this lid down, we can cut the volume in half. When the volume is cut in half, the pressure doubles. So one decreases by a factor of 2, the other increases by a factor of 2. Why does the pressure go up? Well, you're taking the same number of gas particles and you're confining them to a smaller area. And just like the kindergartners, if you cut the size of the room in half, you're going to increase the number of collisions, right, of children running into each other. And so the pressure increases because the gases are colliding with the wall more frequently. Any questions?
This is after their snack?
Pardon me?
This is after the snack? The kindergarten?
Yeah, after the snack would relate more to the temperature changing. Here we have not fed them sugar. So they're just regular. We're just cutting the size of the room. We're squishing them together. But the snack will come later. Boyle's law has applications in scuba diving. So for every 10 meters of depth that a diver goes down, he or she will experience approximately 1 additional atmosphere of pressure due to the surrounding water. So water is a lot more dense than air, and so the pressure increases much more steeply. So at 20 meters, you've gone below the surface 10 meters and 10 meters. Each 10 meters, the pressure increases by 1 atmosphere. The pressure was 1 atmosphere at the surface. You go down 10 atmospheres. It's 10 meters, now you've got 2 atmospheres. You go down another 10, now you've got a pressure of 3 atmospheres. That's 3 times the pressure that you have at the surface. Yes?
Isn't that the reason why there's limitations on what divers can do and what they can be registered for?
Yes. I remember wondering, well, why do you have to take all these classes and get all certified and stuff to do scuba diving? Well, scuba diving is actually quite complicated if you want to stay alive. And that it should be your goal is to remain alive. In terms of the depth and the pressure, the gas needs to be regulated properly as you're breathing. And the type of gas that you use and how fast you ascend and descend, it's all very, very complicated. So when you have an external pressure of 3 atmospheres and you're trying to breathe in air, that's going to cause some problems, isn't it? This doesn't have the one with the straw. I remember watching the Flintstones. This is dating me. When I was growing up, the Flintstones on Saturday morning. But you see this in other cartoons as well. You see somebody underwater and they're breathing air through a really long straw, right? So you can do that if you're close to the surface. If you're 10, 20 meters below the surface, that's not going to work because you're trying to breathe air that's a pressure of 1 atmosphere, but your lungs have to expand against a pressure of 3 atmospheres. Your lungs just aren't strong enough. Your body isn't strong enough to do that. And so that's why divers are breathing pressurized air. So you're breathing pressurized air. If the diver down at 20 meters, 3 atmospheres of pressure that they're breathing, if they were to take a breath and hold it as they rose up to the surface, where the pressure is 1 atmosphere, what's that going to do to the volume of air in their lungs? The pressure now on the outside decreases by a factor of 3. It's going to increase by a factor of 3. The lungs are going to try to expand 3 times. Is that going to work? No. And this is one of the reasons why it's very important for divers to be breathing, inhaling, exhaling as they rise to the surface so that the pressure can equalize and so their lungs don't expand too far and, cause a lot of damage to their internal organs. Any questions? Any of you guys scuba dive? No? It's not a super popular thing here in the valley where there's nowhere to scuba dive. Okay, so how do we use Boyle's law? I actually think this is kind of a difficult first example, but here it is, we'll do it. So a snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at that depth is 7.5 milliliters. What's the pressure? And then we'll ignore the rest of that question for now. So this is a challenging problem. Let's draw a picture and think about what's going on here. So here we have the surface of the water. Up here the pressure is 1 atmosphere. And we take a syringe, and it's got some air in it. Right, so this is 16 milliliters of air. So as I take the syringe lower and lower in the water, what's happening to the pressure on the outside of the syringe? It's increasing, right? So increasing the pressure on the outside is pushing the plunger in, because gases can compress. So we get the syringe down here, and now the volume is less. So the volume down here is only 7.5 milliliters. You can do that with a syringe just by pressing on, it's got to be sealed at the end, but just by pressing on the plunger, you can push it in, right? And then it'll resist and come back out. But going down in the water pressure is causing this gas to compress. So we have a volume up here, and we have a volume down there. So we have two volumes, and we have a pressure up here, and they're asking us what's the pressure down here. So Boyle's law is P1 V1 equals P2 V2. And the ones and twos do not necessarily denote which comes first and which comes second, but they're just, we have two different conditions and we need to get things matched up. So this pressure, 1 atmosphere, goes with this volume because those are the same, they're together. And then down here we have a different pressure and a different volume. For these sorts of problems, it's often useful to make a table to organize the numbers. And so the table is just going to be very simple. And so we've got condition 1 and condition 2. And typically, as you read through the problem, you can pull the numbers out and put them in the table. So snorkeler takes a syringe, 16 milliliters of air. So we'll call that 16 milliliters. So 16 milliliters, is that a volume, a temperature, a pressure? What is that? That's the volume. So I'm going to call this column of my table V. And so 16 milliliters at the surface with the pressure is 1 atmosphere. So 16 milliliters and 1 atmosphere go together. So 1.0 atmospheres. That's a pressure, so I'm going to label that column P. We take the syringe down under the water, and the volume changes to 7.5. So I'm going to put that in my volume column, 7.5 milliliters. And then what typically happens is you've got this little table, and you're going to have one square that's empty. And that should correspond to the question that they're asking you, what's the pressure at that depth? So this is the pressure where the volume is 7.5 milliliters. So this is V1, this is P1, this is V2, and this would be P2. So in here, I'm going to write P2. This is our unknown thing. It's in column P, row 2. So I'm using Boyle's law. I need to rearrange this. I need to solve the equation for P2. This is not the only way to do this problem, but it's the one that works for most students. So if you want to see a different way, ask me outside of lecture. I want to solve for P2. I want to get P2 by itself on one side of the equal sign. So I need to get rid of V2. P2 is multiplied by V2. So what I'm going to do is I'm going to divide by V2. Because V2 over V2 is 1. It cancels out. In order for this to remain an equality, though, I have to do the same thing to both sides. You can think of a math equation as being like a balanced teeter-totter, right? And so if I do something to one side of the teeter-totter and I want it to stay balanced, I need to do exactly the same thing to the other side. So if I divide one side by V2, I need to divide the other side by V2. You have learned how to do this in the past. You may have forgotten, but you did learn this at some point. And we're going to have to do a lot of this. So if this is something that's difficult for you, and that's actually pretty common in this class, please get some help from me or from somebody else. It's really important to be able to rearrange simple equations. So now I've got my equation. P2 is equal to P1 V1 divided by V2. There's a lot of similar letters and numbers, so be very careful that you're copying them correctly. I've got my equation, I've got my numbers, I'm just going to plug them into the equation. Always include the units. So I look in the table for P1, and I see it's 1 atmosphere. And then I need volume 1, and that is 16 milliliters. And that's divided by volume 2, 7.5 milliliters. So I do the math. 16 divided by 7.5. And my calculator says 2.13 forever. Look what happens with the units. The milliliters are going to cancel, and I'm left with atmospheres. In terms of significant figures, how many sig figs should this number have? 2. So the pressure I would express as 2.1 atmospheres. So that's the answer to the first question. Any questions? I think this is a difficult first example for a gas law problem, but this is not a difficult problem for Chem 1A. There are a lot of word problems, and we need to learn how to deal with them. The thing is that life is full of word problems, right? So we just need to learn how to translate the words into a math equation. Usually you're fine with the math equation, just give me the equation, I can solve that. But how do you get the words into the equation? That's a skill we need to work on. Okay, so there is another question, right? And this is one of my pet peeves as an instructor. If there are 2 questions, you better give me 2 answers. Okay? Sometimes it's like labeled question number 1, but there's actually 2 or 3 questions in there. You better give answers for each of them. And that's something that could be important, say, on a job interview. Right? I get to be on hiring committees, and you see an applicant who doesn't follow the instructions filling out the application. They don't answer all the questions. Where does their application go? In the trash. Because you've got all these other people that can at least fill out the application correctly, so you're going to spend your time evaluating them instead. So the second question, how deep is the snorkeler? Okay, this one requires a little more thought. Well, what did we learn? Every 10 meters, right? Every 10 meters, the pressure increases by 1 atmosphere. So at 10 meters, the pressure is 2 atmospheres, right? So this is 2.1 atmospheres. It's a little more than 10 meters, right? So we can make up a conversion here. What is the difference between this and the pressure at the surface? 1.1, right? The pressure at the surface is 1 atmosphere, and the pressure down here is 2.1. So the increase in pressure is 1.1 atmosphere. Pressure increased 1.1 atmospheres. You okay with that? We get 1 atmosphere for every 10 meters. So we can make that into a conversion factor. 1 atmosphere per 10 meters, or 10 meters per 1 atmosphere. So if we look at the increase in pressure, we can use this factor, one of these factors, to figure out the depth. So an increase of 1.1 atmospheres, I'd want to put atmospheres in the bottom and meters on top, 10 meters for every 1 atmosphere. And so that ends up being 11 meters. So the snorkeler has descended to 11 meters below the surface. Any questions? Another scientist who studied gases was J.A.C. Charles. He lived in the 17 and 1800s. He looked at the relationship between the volume of a gas and its temperature. And he found that the volume of a gas is directly proportional to its absolute temperature. We'll talk about what that means in a minute. So Charles' law, volume is proportional to temperature with constant pressure and amount of gas. And so we can express this as the volume divided by the temperature is equal to a constant, or what's more useful for our purposes is V1 over T1 is equal to V2 over T2. The absolute temperature is important. We need to use the Kelvin temperature scale. So anything that we're doing with gases, the temperature must always be expressed in kelvins. They will typically give you the temperature in Celsius. You have to change it to kelvins. Sometimes they want the answer in Celsius, then you have to change your Kelvin answer back into Celsius to report it. But when you're doing the calculation, it has to be in kelvins. So here's an example of some data demonstrating Charles' law. Volume on the y-axis, and now we're changing the temperature. So here there's different lines. For 1 mole of gas at a pressure of 1 atmosphere, this is the relationship between volume and temperature. If we change the amount of gas but keep the pressure constant, we see that we get a different slope to our line, but the line is still a line, it's still proportional. What we observe about these lines is that they all intersect at a particular point. They intercept where the volume is 0, and that corresponds to a temperature of minus 273.15 degrees Celsius. That temperature is called absolute 0 and is the basis for the Kelvin scale. That's 0 Kelvin, which kind of looks like okay, but it's 0 Kelvin. That's the absolute temperature, absolute 0. This is absolute 0 because what this data predicts is that if you went lower in temperature, the volume would become negative. Is it possible to have a negative volume? No. You get down to no volume and that's where things stop. So this is the lowest temperature possible. No, it's not there. Okay. So the reason we need to use the Kelvin scale is because on the Kelvin scale, we will never have negative temperatures, right? Because it will not go below 0 Kelvin. The Celsius temperature scale, you can end up with 0 as your temperature or less than 0, negative temperatures. And then when you put that into an equation like this, if you have 0 for a temperature, what's that going to do to this? You can't divide by 0, it's undefined, right? So the Celsius scale does not work for gas laws. We need to use the Kelvin temperature scale. So let's look at what's happening to the molecules here. And this is something you could try at home. Take a balloon, stick it in ice water, watch it shrink, and stick it in boiling water and watch it expand. What's going on here? Same number of gas particles, but in the cold environment, the gas particles have lower kinetic energy. They're moving more slowly. And so they're bouncing around here, exerting a pressure. Over here, they have higher kinetic energy, and so they're going to be moving faster. They'll collide more frequently with the walls and with more force, and so they will exert a larger pressure. Here, the pressure is allowed. The pressure is going to end up being the same, and so what that happens is then the gas expands, the balloon expands. That didn't go very well. Any questions? So you increase the temperature, the gas particles move faster. So the collisions with the wall are more frequent, the force exerted with each collision is greater. In order for the pressure to remain the same, the gas must expand into a larger volume. We'll see this relationship with temperature and the movement of particles. And one way to remember that is to think about barefoot people on the beach. So if you go to Reedley Beach right now, did you know there's a beach in Reedley? There's a beach in Reedley. It's a nice sandy beach. It's on the river. Right now it's mostly beach and there's almost no river, but there is a beach in Reedley. So big sandy area. Right now, you can walk barefoot on the sand and you'll be just fine, right? Because the sand's cold. So you go there in July when it's 106. Can you stroll barefoot on that sand? No. You're going to go from your chair or wherever your shoes are, and you're going to, we say, hot-foot it, right? You're going to walk very quickly to the water, right? Because it hurts. People walk very quickly on hot sand, right? So hot gas molecules move very quickly, just like people on hot sand. And on the cold sand, you move more slowly. So in July, if you want to, really enjoy the beach, where do you go? You go to the coast. You go to Pismo, right? Where it's cold in the summer, and you can freeze, right? It's a Central Valley thing, isn't it? Okay. So here's a picture of a balloon sitting. I think this is dry ice, so it got very cold. So you get this big balloon, and you make it cold, and it shrinks. Charles Law also explains why hot air balloons work. I remember being really puzzled by this as a child because, as a child you learn that, well, if you blow up a balloon with your mouth, just putting air into it, it's not going to float, right? Only the cool helium balloons that you had to pay money for float. So here's a balloon that not only doesn't have helium in it, but it's got this giant hole at the bottom. How the heck is that floating, right? Well, it has to do with this big shooting flame here, right? It's got this big old burner here that heats the air. When you heat the air, what happens to its volume? It expands, right? So when the volume expands, what does that do to the density of the gas? The density goes down. Helium balloons float because the density of helium is less than the air surrounding them. Hot air balloons float because the density of the hot air is less than the cold air around it. Yeah. That's a good question. Does pressure come into this at all? It does somewhat, because as the balloon rises, the pressure of the atmosphere is less, and so then this density causes it to be even more buoyant. But then the temperature also falls at higher altitudes, so you've got that going on.
So then would you compare it with like Alt V, or would you just compare it?
Well, so the thing is that because this balloon is open at the bottom, the pressure of the gas inside is equal to the pressure outside, right? There can't be a pressure difference if they're open to each other. So the pressure difference is zero. The pressure inside is the same. But because the gas particles are moving faster at a higher temperature, the volume is larger, causing them to be less dense. It's all interrelated. So let's do a Charles Law problem. Gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 Celsius to 155 Celsius, what is its final volume in milliliters? So this is more of a very straightforward type of simple gas law problem. So again, I would encourage you to make a table and collect the numbers. So we'll have 2 rows, and we'll label the first one 1 and the second one 2. And then just go back through the problem. So I come to a number, 88.2 milliliters. So I'm going to write that down, 88.2 milliliters. Then I ask myself, well, what quantity is that, P, V, N, or T? Well, it's V, right? It even says volume of. If it doesn't tell you that's the volume, the unit should tell you milliliter is a unit of volume. So that's my volume column. So that's the initial volume, and then it says we're heating the gas from 35 to 155. So this is the temperature that we're starting at. This is the initial volume, so those go together, 35 degrees Celsius. And the other one is 155. And then we're asked, what's the final volume? And we conveniently have a blank here for volume, V2, and that's what we're going to be looking for. What do we have to watch out for in this problem? Celsius. Okay? So when you first write these down, just convert them to Kelvin, because you're going to have to. If you do it right away, there's less chance of forgetting. So plus 273 plus 273. So 35 plus 273, 308. And 428. So we've got to use Kelvin. Okay, so we've got our stuff all identified here. We're using volume and temperature, so we need the Charles law expression V1 over T1 equals V2 over T2. Yes?
Why don't you do 273.15?
That's an excellent question.
Not a big difference, but
Yeah, so why did I do 273 and not 273.15? 273.15 is better. The book is kind of sloppy on this and does 273 for a lot of these things. In this instance, it's not actually going to make any difference because our temperatures were only to the nearest 1 degree. I think it is better to do 273.15. Yeah. So I've got this. This is an equation that is fraught with peril because it has fractions in it. I would encourage you to get rid of the fractions first before you try to rearrange it. Because people do very, very unfortunate things when they rearrange these. So to get rid of the fractions, let's cross multiply. So cross multiplying says I'm going to take the top of one side times the bottom of the other side. And that's going to equal excuse me, the bottom of the first side times the top of the second side. Now, some of you are really great with algebra, and you can just rearrange this in your head. That's awesome. I'm talking to the people who can't do that. So top of this side times the bottom of that side equal to the bottom of this side times the top of that side. I got rid of the fractions. So now I can look at this and say, well, what was I trying to find? I'm trying to find V2. Okay, so now I can isolate V2, divide by T1. If I do that to one side, I have to do it to the other side. And so there's my equation. V2 is equal to V1 T2 over T1. Always, double check. Those 1s and 2s are so easy to mess up. Okay, so volume 1, 88.2 milliliters. And that's times temperature 2, 428 Kelvin. And then I'm going to divide by temperature 1, 308 Kelvin. Look at the units. The kelvins cancel out. And so I'm going to end up with milliliters as a volume unit, which is good. So my calculator says 122.56 milliliters. All these numbers have 3 sig figs, so my answer should have 3 sig figs, and we're going to call that 123 milliliters. Yes?
I did it a different way.
Mm-hmm.
Multiplied it by T2 on both sides, and I got the same answer.
Yeah.
Would it give me different answers, though, eventually? Or would it...
If you do your math correctly, you'll be fine. My experience, especially if we're trying to solve for T1, I've already seen it with this class and density, solving for volume in the density equation. People do things that aren't correct with the algebra, and they end up with 1 over V and calling it V. So yes, you can just take this equation, multiply both sides by T2, and you get this exact same equation. You just have to be careful with your algebra. Any other questions? On the simple gas laws, we can also ask ourselves, well, is this answer reasonable? So what did we do here? We increased the temperature of the gas. Do we expect the volume to be bigger or smaller? Bigger. And our volume was bigger, so that's encouraging, right? Because if you get your 1s and 2s backwards, you could end up making the volume smaller, and checking the reasonableness at the end might save you from getting that one wrong. Any questions? Amadeo Avogadro he was born the same year our country was born, 1776. He was the first one to formally state the relationship between the volume of a gas and its amount in moles. So what he determined is that the volume of the gas is proportional to the number of gas molecules. This is an odd thing about gases. It's not proportional to the mass of the gas, it's proportional to the number of particles. So we can express Avogadro's law as volume is proportional to N at constant T and P, or this way, V1 over N1 equals V2 over N2. The amount of gas is measured in moles. Equal volumes of gases contain equal numbers of molecules. What the gas is doesn't matter. And we'll see why that is later. So here's a graph of some data showing Avogadro's law. The volume of a gas increases with the number of moles of gas is directly proportional. And that makes sense, right? You take a balloon and you put more air into it, you expect that the volume is going to increase, and that's what it does. If we extrapolate to 0, we find that this predicts that at 0 volume there would be 0 gas molecules. That makes sense, right? Okay, here's an Avogadro's law problem. Chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.12 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? We're going to assume constant pressure and temperature, not temperatures, and that the initial amount of gas was completely reacted. Well, we're going to make a table. We're going to have 1 and 2. Go back through the problem, pick out the numbers. 0.621 moles of product that is a gas. 0.621 moles. So I had 4 variables, P, V, N, and T. Which one is this? N. N is moles of gas. And it says the cylinder contained 0.12 moles of gas before the reaction. Okay. So you may be thinking, well, but this was before and this is after. You've got them backwards. It doesn't matter as long as you keep them together. Had an initial volume of 2.18 liters. So this volume, oops, somebody broke glass. Common sound around here. This volume goes with 0.12 moles or 0.621 moles? The 0.12, okay? So you read the problem, it contained 0.12 moles before the reaction and had an initial volume. So that tells you that those two numbers go together. So I've got those on the same row. This column is V for volume. It's asking me what the volume is after the reaction, and that would correspond to this blank in my table. Volume 1 over N1.
Wouldn't it be V1?
Yeah, it would be. Sorry. Thank you. I was trying to test you to see if you were paying attention. No, I wasn't paying attention. Yes, that's V1. So this is V1, because this is V2. So this is Avogadro's law. And again, we have fractions here. We're trying to solve for V1. So it's not too bad rearranging this. But still, I'm going to encourage you to cross-multiply, get rid of the fractions. V1 N2 equals N1 V2. And then I'm going to divide both sides by N2. So you may rearrange this equation any way you like, but we should end up with the same thing. Okay? Got the equation, plug the numbers in. You need to show your work when you do these problems. Okay? So what do I mean by showing your work? The minimum for showing your work is write the equation with the numbers and the units in there. Yeah? That's an excellent question. So I am trying to find the volume after the reaction. So it seems logical that would be V2. But the way I made the table, the volume after has the subscript 1. The 1 and the 2 do not mean before and after. They just mean one condition, the other condition. And if you can definitely just, if you really want this to be V2, the simplest thing would be to just switch these numbers, and that would work absolutely fine. Good question. So N1, V2, and divided by N2. I look at my units, the moles cancel out. I do the math, 0.621. Yeah.
So we don't convert moles into number of particles using Avogadro?
No, we don't have to go to numbers of particles because moles are directly proportional to numbers of particles. Otherwise, we end up with some really giant numbers, which would still work, but it's not necessary. 0.621 times 2.18 divide by 0.12. 11.2815. And that's going to be liters. All of my numbers had 3 significant figures. Whoops. So this should have 3 sig figs. Round that to 11.3 liters. Then we ask ourselves, well, does that make sense? Well, before the reaction, I had 0.12 moles. After, I've got 0.62 moles. So I have more gas. Is that going to occupy a larger volume or a smaller volume? Larger volume. And the volume went up. It went from 2 to 11. So the right direction. Any questions? Another example. This is a little more involved. So scale model of a blimp rises when it's filled with helium to a volume of 55 cubic decimeters. when 1.1 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant T and P. This class requires you to do some critical thinking. And solving a problem like this involves some critical thinking. There will be problems on the exam that are very different from anything that we've done in lecture, in lab, or in the homework. And this would be an example, just like coming out of nowhere. What the heck? Different units, blimp, what's going on here? So we got to think about this. So we've got this blimp, and it will rise when the helium in it has a volume of 55. So I'm going to draw the blimp. Kind of looks like a fish. So this is the blimp when it's floating, and the volume is 55 cubic decimeters. So down here, I've got the blimp. It's kind of, squishy and flat down here. So we put 1.1 moles of helium into the blimp. Started out flat. And the volume is 26.2 cubic decimeters. Now, cubic decimeters is a unit that we haven't used very much. But, cubic centimeters, cubic meters, it's a volume unit. It's okay. So that's the volume, and this is the amount of gas in moles. So this is partially full. We need to fill it up to 55 cubic decimeters to make it float. So I have volume, and amount of gas in moles. I could probably calculate what the amount of gas in moles is up here. Right? Does that make sense? That's not what the question's asking me for, but Avogadro's law would let me calculate that. So this is, what is this? So let's try this one without a table. So I drew my pictures here, and I'm going to call this V1 and N1, and I'm going to call this V2 and N2. And I could calculate the amount of moles of gas when it's floating, right? So Avogadro's law. And I'm going to solve for N2. So this is where the cross-multiplying really comes in, because students will do, I'm not going to illustrate because that would encourage it. Anyway, V1 N2 equals N1 V2. Cross-multiplying to get rid of the icky fractions. Divide by V1 on both sides. So the amount of gas when it's floating is going to be equal to N1 V2 over V1. 1.10 moles. Volume 2 divided by volume 1. And what happens to that icky cubic decimeter unit? Cancels out. 1.1 times 55 divided by 26.2. So N2 equals 2.3091 moles of helium. So yay, we calculated something. Is that the answer to the question? No. Now we know the total amount of moles that we need to get in here. They're asking how many more grams do we have to add? Well, we started with 1.1 mole. We need to end up with 2.3091 moles. So we could figure out how many moles of gas need to be added, right? And then we can look up the molar mass of helium and convert that to grams. So we take the 2.3091 moles, subtract how much was in there to start with. So that's going to be 1.2091 moles. So this is moles that we need to add. It's not our final answer there, but it's getting there. 1.2091 moles of helium. And I'm going to convert that to grams, multiplied by grams, divide by moles. Periodic table says 4.003 grams of helium per mole. $4.8402 grams. Round that to 4.84 grams of helium. Any questions? These critical thinking problems will involve things that we have learned, but you have to take these individual pieces and put them together in a way that you haven't been shown. So here we're combining a molar mass conversion with an Avogadro's law problem. Any questions?